The scene begins with a silence so deep it feels ancient. A silence that has never known wind or water, never felt the warmth of a dawn. Out here, in the dark beyond the last thin breath of sunlight, a lone machine drifts through eternity. It is small against the void, no larger than a family car, yet wrapped in an armor of gold. On its side, a disk the color of sunlight at dusk carries the memory of a world it will never see again, the whisper of oceans breaking on distant shores, the laughter of children who will never grow old, the heartbeat of an entire species captured in grooves of copper and gold. It is Voyager. For nearly half a century, it has been falling outward, beyond the planetary family that once pulled it close. It has crossed the heliopause, the invisible frontier where the sun's breath yields to the winds of other stars, and entered a realm no human has ever touched. Still, it speaks. Its voice, a faint ripple of radio waves, crosses the black in a journey lasting over 20 hours at the speed of light. On Earth, vast metal ears, dishes spread across mountains, deserts, and plains, bend toward that whisper, catching each word before it fades into the static of the cosmos. One day soon, the whisper will stop. The last syllable will arrive, carrying a final measurement of the void, a ghost from a ship older than many of those listening. And when that moment comes, humanity will stand at the very edge of a truth it cannot yet name, staring into the first unbroken horizon of the deep, black ocean beyond the sun. In the late summer of 1977, at the height of the Cold War, two machines sat poised on the launch pads of Cape Canaveral, their metal skins gleaming in the Florida sun. They were twins, but not identical in their fates. Voyager 2 would depart first, on August 20th, followed by Voyager 1 16 days later. Their destination, the unexplored outer reaches of the solar system, worlds that had until then been little more than blurry photographs in astronomers' archives. They were emissaries of Earth, born from an age when the superpowers stared each other down across oceans and ideologies, yet still found common ground in a shared hunger to know the unknown. This was the 1970s, an era when the hum of teletype, machines and the grainy glow of cathode ray screens carried whispers of distant missions. The Vietnam War had ended, the Apollo program had drawn its last breath, and the future of space exploration hung in a fragile balance between political will and scientific ambition. Yet, in the midst of this uncertainty, a rare celestial event opened a door that would not swing wide again for another 176 years. For giant planets Jupiter, Saturn, Uranus, and Neptune had aligned in such a way that a single spacecraft could visit them all, using each world's immense gravity as a slingshot to hurl itself toward the next. This was the Grand Tour, a dance of orbital mechanics choreographed not by human hands, but by the deep clockwork of the cosmos itself. The Voyagers were not built to last forever. They were designed for 5 years, for the rigors of planetary encounters, not the eternal cold of the void. Each carried a suite of instruments, cameras, spectrometers, magnetometers, plasma detectors delicately calibrated to read the subtle whispers of alien atmospheres and the invisible tides of magnetic fields. And each carried something else, something deeply human. A gold-plated phonograph record, encoded with the sounds and images of Earth, conceived by a committee led by Carl Sagan. The golden record was both an archive and an offering, containing greetings in 55 languages, the calls of birds and whales, the rush of wind and surf, and the music of cultures separated by continents and centuries. It was a time capsule meant not for our descendants, but for strangers who might never know our world except through these fragile grooves. Guiding the mission from its inception was Ed Stone, a physicist who would become its steady voice for decades. He was there when the spacecraft were sealed in their fairings, when they pierced the blue canopy of Earth's sky, when they turned their cameras back toward the home planet for the last time. Stone and his team knew they were crossing a threshold in exploration, not merely visiting new worlds, but sending machines into an environment no probe had ever touched. For beyond Neptune, beyond even the most distant of known comets, lay the heliopause, the invisible frontier where the solar wind, racing outward from the sun at supersonic speeds, finally yields to the pressure of the interstellar medium. It was a border written not in stone or treaty, but in plasma and magnetism shifting. Elusive boundary no spacecraft had yet crossed. The Voyager's journey outward would be one of revelations and of unintended fates. They would show us the volcanic heart of Io, the braids of Saturn's rings, the deep blue winds of Neptune. But long after the encounters were over, after the cameras shut down and the planetary flybys became memories archived in data vaults, the Voyagers would keep going. They would pass beyond the sun's magnetic shield into a realm where the space between the stars is not empty, but alive with the thin breath of cosmic rays and the ghostly fields of ancient supernova. No one could have known, in that summer of 1977, that these machines would become the first of our creations to enter interstellar space, carrying with them a whisper of Earth across a gulf so vast it can only be measured in light years. The two Voyagers, now well beyond the inner planets, began to pick up the whispers of the giant worlds ahead. Jupiter loomed first, a titanic magnetosphere, a planetary storm system larger than the Earth itself, and a retinue of moons, each with its own story carved in ice or stone. The alignment that had been calculated years earlier was now a tangible reality unfolding in the cold, silent ballet of celestial mechanics. The gravitational pull of Jupiter was not simply a hazard, it was a slingshot, a cosmic catapult that bent each probe's path and flung it onward with newfound speed. Beyond Jupiter, Saturn waited, its rings glinting in the distant sunlight like a frozen halo. Here Voyager revealed worlds within worlds, the hexagonal storm at the planet's pole, the geysers of Enceladus, the complex braiding of ring particles guided by invisible shepherd moons. For scientists on Earth, these images were a kind of time machine, revealing environments that had existed untouched for billions of years. The sense of awe was tempered by precision, each encounter measured, each photograph catalogued, each reading stored for the long transmission home. From there, the trajectories began to diverge. Voyager 2's path, by design, would lead it toward Uranus and Neptune worlds so distant that their surfaces had never been seen in detail by human eyes. Voyager 1, flung on a steeper path, would bypass them entirely, setting it on a faster route toward the outer edge of the Sun's dominion. The mission planners had known this when they charted the courses, but what no one could have known was how long the spacecraft would endure. Uranus emerged like a pale turquoise marble in the darkness. Voyager 2's flyby in January 1986 revealed a world tipped on its side, its axis lying nearly in the plane of its orbit. The result was a strange and alien system, where seasons lasted decades, and sunlight grazed the poles in ways no other planet experienced. Its atmosphere, bland to telescopes on Earth, betrayed subtle patterns under Voyager's gaze winds, rushing through frigid clouds of methane and hydrogen. The probe also uncovered moons, scarred by ancient collisions, their surfaces etched in a cryptic geological script. Then came Neptune in 1989, a deep azure sphere, distant and cold, its atmosphere alive with unexpected tempests. A storm system the size of Earth spun in the southern hemisphere, dark and turbulent, framed by high white clouds moving at speeds unmatched in the solar system. Neptune's largest moon, Triton, startled scientists with active geysers venting nitrogen into space. This frozen, captured world hinted at a restless interior, warmed by forces not yet fully understood. It was a fitting finale to the planetary tour of discovery at the very edge of what sunlight could reach in strength. But after Neptune, no more worlds awaited in their planned itinerary. The Voyagers had completed their prime mission. What lay ahead was not mapped in the same detail. Open road stretching beyond the last major planet, into the domain of dust, radiation, and the fading breath of the sun. It was here that their unintended destiny took shape. Their instruments, still functioning, could measure the solar wind as it weakened and thinned, and record the shift in charged particles as they moved closer to the heliosphere's boundary. The heliopause, the invisible frontier between the sun's influence and the raw interstellar medium, had never been reached by any spacecraft. The term itself sounded almost mythic. A pause, a breath, a moment before crossing into the great unknown. Scientists understood it as the place where the outward pressure of the solar wind met the incoming pressure of particles from the galaxy beyond. The distance to this boundary was uncertain. Estimates varied from 150 astronomical units from the sun. The Voyagers were heading straight for it, but no one could predict exactly when or what they might find on the other side. In this quiet transitional phase, human attention shifted from the spectacular to the subtle. Instead of color photographs of planets, data now came in the form of magnetic field readings, plasma measurements, and counts of high-energy particles. It was a shift from the visual to the invisible, from landscapes to fields and forces. Yet there was a poetry in these numbers, a whisper of change, a sense of movement toward a frontier that was both physical and symbolic. Back on Earth, the mission leadership evolved. Ed Stone, who had been project scientist from the beginning, continued to guide the mission for decades, providing continuity through the passing eras of technology and culture. Around him, a team of engineers and scientists worked to keep the aging spacecraft alive. The hardware was built in the 1970s, its computers weaker than a modern pocket calculator. Yet, it had proven astonishingly resilient. Small course corrections were made using thrusters that had not fired in decades, their tiny puffs of gas, still capable of changing orientation across billions of kilometers. And then there was the golden record, Carl Sagan's enduring contribution. Attached to each Voyager was a copper disc, plated in gold, etched with sounds and images chosen to represent Earth to any who might find it. Greetings in dozens of languages, music from across cultures, natural sounds like wind and thunder, and a collection of photographs depicting life on our planet. The record was a gesture at once humble and grand, a message in a bottle cast into a cosmic ocean whose shores might never be reached. Sagan had insisted that even if no one ever heard it, the act of sending it mattered. It was a reflection of how humanity saw itself in that moment as species reaching outward, hopeful that the universe might listen. By the late 1990s, the Voyagers were deep into the Kuiper Belt, that vast ring of icy debris left over from the formation of the solar system. Here, sunlight was so weak that it resembled a bright star rather than a life-giving disk. Temperatures plunged toward absolute zero, and time seemed to stretch in the stillness. Yet the spacecraft pressed on, propelled not by engines but by inertia, their radio signals still finding their way home after traveling for more than a dozen hours across the gulf of space. As the 21st century dawned, the boundaries of human presence had quietly shifted. These two machines, built with the technology of the typewriter era, were now farther from Earth than any other objects made by human hands. The Cold War that had been the backdrop to their launch was over, but their journey continued, indifferent to the changes on the planet they had left behind. They were emissaries not just of a nation, but of an entire species, carrying within them both data and dreams. The seed of the mystery was planted here, in this long interlude between worlds. If the heliopause was ahead, somewhere in the darkness, what would its crossing reveal? Would the interstellar medium be as models predicted, a thin soup of charged particles, magnetic fields, and cosmic rays? Or would it hold surprises, signatures of processes not yet imagined? The only way to know was to keep going, to wait, to listen. Year by year, the readings shifted. Particle counts fluctuated, magnetic fields wavered, and scientists argued over the interpretation. Was the boundary near or still far? There were false alarms moments when changes in the data seemed to suggest the crossing had happened, only for later analysis to show otherwise. The Voyagers themselves offered no drama, no signal of triumph. They simply continued to send what they saw, unblinking, across the dark dot in time. The day would come when one of them, Voyager 1, would slip through the heliopause, silently entering interstellar space. But in the late decades of the 20th century, that moment was still ahead, veiled in uncertainty. For now, they were travelers on a road no other probe had taken, carrying with them not just instruments, but the echo of human curiosity, an echo that would one day reach beyond the sun's protective breath, into the cold and star-filled night that stretches forever outward. The late 20th century was a time when even the boundaries of the sun's dominion remained a sketch in the minds of scientists. Telescopes, for all their reach, could not reveal the edge of the solar system. The planets had been mapped. Their moons had names and histories. But the boundary between the sun's breath and the interstellar dark was not something one could sit, was an idea, an abstraction. Astronomers called it the heliopause, a place where the outward wind of charged particles from the sun would weaken, falter, and finally yield to the invisible tide flowing from the galaxy beyond. No human-made object had ever gone so far. The edge was not merely a location. It was a frontier in the purest sense, a threshold between worlds. The concept of the heliosphere was still young. Researchers imagined it as a vast, teardrop-shaped cocoon inflated by the sun's magnetic field and the steady stream of plasma known as the solar wind. This wind, born in the furnace of the sun's corona, raced outward at hundreds of kilometers per second, carrying with it a magnetic field that could shield the solar system from much of the galaxy's radiation. Yet, like any breath, it could not blow forever. Somewhere, far beyond Pluto, the solar wind would slow to a crawl under the pressure of the interstellar medium, a sea not of water, but of particles and magnetic fields, ancient remnants from exploding stars, cosmic rays older than the Earth itself. Scientists spoke of it in terms both precise and poetic, an invisible shoreline where one ocean met another. The strangeness of this boundary lay not only in its distance, but in its nature. Space beyond the planets was not the empty nothing of schoolroom diagrams. It was alive with energy, The interstellar medium swirled with charged particles traveling near the speed of light, with magnetic turbulence that could twist a compass needle into madness, and with dust grains older than the sun itself. Each particle carried a history, a record of supernova that had seeded the galaxy with heavy elements. To cross into this domain was to step into the bloodstream of the Milky Way, yet the question hung like a shadow over the Voyager mission. Could the spacecraft endure long enough to find that place? Designed in the 1970s, their instruments were already modest, even at launch. Their computers had less memory than a modern wristwatch. Their sensors, built to measure planetary magnetospheres and plasma fields, might not even register the subtle changes at the heliopause. The journey could take decades, and the outer darkness was unforgiving. Radiation could cripple electronics. Micrometeoroids could strike without warning. The greatest uncertainty was time itself, whether humanity's patience could last as long as the machines would need. Among scientists, there was hesitation. Some doubted whether the heliopause could be detected at all. Others believed it was so far away that Voyagers 1 and 2 would fall silent before ever reaching it. But there were those who saw in this mission something greater than measurement. Alone, they imagined the Voyagers as emissaries, not just machines, but symbols of a young civilization testing its reach. If they crossed the boundary, they would be more than interplanetary probes. They would be interstellar envoys, carrying the voices of Earth into the dark. And beneath the technical debates ran a deeper, older question, one that stretched back to the first explorers who set sail from familiar shores. Could a creation outlive its makers? Could a fragile construct of metal, wire, and code endure long enough to deliver its message to a place no living human had seen? For the scientists watching from Earth, the prospect was humbling. The Voyagers might travel farther than the memory of those who built them, outlasting names, nations, and perhaps even the species that gave them birth. In the cold clarity of the void, they would not know loneliness. They would only know the path ahead. It was in dimly lit conference rooms and cluttered offices that the first true debates took shape. Charts sprawled across tables, speckled with ink and pencil marks, showing the solar wind's velocity, density, and magnetic field strength. The data from Pioneer 10 and 11 precursors to the Voyagers hinted at a vast decline in solar wind pressure with distance. But the numbers were incomplete, fragmentary, like notes from a song heard through a wall. Extrapolations placed the heliopause anywhere from 50 to 200 astronomical units away. It was as though sailors of the Age of Discovery had been told that the edge of the ocean might be a week's sail away, or it might be years. No. One could be sure the interstellar medium itself was a riddle. Its density, about 1 atom per cubic centimeter, was so tenuous it might be mistaken for emptiness, yet it could slow and even halt the solar wind. Its pressure was shaped not just by the gas between the stars, but by tangled magnetic fields stretching across light years, relics of violent cosmic events. Each new model introduced new uncertainties. Was the heliopause smooth and rounded, or wrinkled and unstable, warped by magnetic turbulence? Was there a bow shock ahead of the sun, like the wave before a ship's prow? Or would the sun's motion through the galaxy create a quieter, subtler boundary? The answers would remain hidden until a spacecraft could wander that far. Inside NASA's Jet Propulsion Laboratory, the mood was a careful balance of optimism and restraint. Voyager's original mission had not been built for interstellar space. It had been conceived to study Jupiter and Saturn, with a possible extended journey to Uranus and Neptune. Every additional year beyond that was a gamble. The instruments were robust, but finite in capability. Power came from radioisotope thermoelectric generators, steady, reliable, but destined to fade as their plutonium cores decayed. In the 1970s, it was easy to imagine the spacecraft falling silent somewhere in the cold between Neptune and the unknown edge. A final transmission fading into static dot. Still, there were voices who urged patience. Time, they argued, was not the enemy in such an endeavor, it was the essence of it. The heliopause was not a goal that could be rushed. To find it required waiting, listening, and letting the solar wind carry the craft outward. Even if the crossing never came, the data gathered along the way would transform the understanding of the outer solar system. Already, Voyager was teaching scientists that the solar wind varied in ways not fully predicted. It ebbed and flowed with the sun's activity cycle, and its composition shifted with solar storms, sending shockwaves racing outward for billions of kilometers. These disturbances, too, might someday be felt at the edge. By the early 1980s, new magnetic field models suggested that the sun's protective bubble might be more compressed than previously thought, squeezed by a denser-than-expected interstellar medium. If true, Voyager could encounter its edge sooner than anyone dared hope. Others warned that such projections were built on sparse data, more a reflection of human desire than cosmic reality. Still, the idea that the crossing might happen within a human lifetime began to take root, and with it came a quiet thrill, the knowledge that if the spacecraft endured, humanity might witness a boundary crossing, not in myth or metaphor, but, in fact, the philosophical weight of the mission began to press on the minds of those involved. In the sterile glow of control rooms, surrounded by telemetry screens and printouts, the scientists could not escape the sense that Voyager was more than a tool. It was a question launched into the dark. How far can we go? Could an artifact of Earth carry meaning in a place where no eye, human or alien, might ever see it? If it crossed into interstellar space, the event would not change the course of galaxies, but it would mark, in the quiet ledger of the cosmos, that a species once bound to a single world had sensed something of itself, beyond the reach of its own star. Even in the broader scientific community, the idea of a solar system boundary was met with a mix of fascination and skepticism. In public lectures, astronomers would draw the heliosphere as a great glowing bubble, its outer skin shimmering against the black sea of interstellar space. But in private, they admitted that no one knew what that skin truly looked like. Some suspected it might not be a clean surface at all, but a messy transition zone, a fog of mingling particles where the solar wind gradually lost its dominance to the galactic environment. In such a place, Voyager's instruments might not detect a sudden change, but a slow drift into difference, a faint shift in the rhythm of particles, like hearing a new instrument join a symphony. This uncertainty was magnified by the limitations of the technology itself. Voyager's plasma detectors could measure the speed and density of charged particles, but only if those particles were moving in certain directions relative to the spacecraft. Its cosmic ray detectors could sense high-energy particles from beyond the sun's reach, but interpreting those readings required careful disentangling from the effects of solar activity. The magnetometer's delicate coils of wire and electronics could feel the whisper of magnetic fields, yet they too would record subtle, gradual shifts rather than dramatic reveals. In essence, Voyager might cross the boundary without any single moment announcing it. Still, The pursuit of that moment became a quiet undercurrent in the mission. In scientific journals, papers began to appear with cautious phrases, potential heliospheric boundary detection, or possible evidence of interstellar modulation. At conferences, younger researchers would gather in corners, sketching possible scenarios on notepads, imagining the data curves that would prove the crossing had occurred. To them, the quest was not merely technical, it was a chance to be part of an event that would echo in history books long after the individuals were forgotten. As the years passed, Voyager's survival began to feel less like an engineering achievement and more like a kind of endurance ritual. Each new data downlink, every faint whisper from billions of kilometers away, was a reassurance that the spacecraft still drifted outward, still listening to the winds of the sun. The mission team learned to live in long stretches of silence, punctuated by the arrival of numbers and graphs that spoke of worlds and spaces no human eye would ever see. By the late 1980s, some scientists began speaking of the mission in terms that blurred the line between exploration and legacy. The golden record, bolted to Voyager's side, had always been intended as a symbolic gesture, time capsule for hypothetical beings who might one day intercept the craft. But as the spacecraft pushed deeper into the darkness, the record's presence began to feel like a statement of intent. Voyager was no longer just a probe. It was a messenger, bearing the first physical greeting from humanity to the galaxy. Yet, the scientists remained careful not to romanticize too much in their work. Their papers stayed grounded in numbers, error bars, and probabilities. The heliopause was still an estimate, the interstellar medium was still a model, and the spacecraft, though remarkable, was still subject to the decay of its own heart. The plutonium core would cool, the power would fade, the instruments would one by one fall silent. Whether Voyager would survive long enough to reach the boundary was still a question without an answer. But somewhere beneath that discipline there was the quiet hope that it might. And in that hope was something deeply human, the desire to leave, a mark in the unknown, to plant not a flag, but a question on the farthest edge of the sun's reach, in the control rooms and offices of NASA's Jet Propulsion Laboratory. The passage of time was measured not in days or weeks, but in the widening gulf between the Voyagers and the sun. Every new astronomical unit, extra 150 million kilometers, was a step deeper into the void. By the early 1990s, the spacecraft had traveled so far that the light from the sun took over 9 hours to reach them. And yet, even at such distances, the heliosphere still stretched ahead, an invisible shield that guarded the planets from the full fury of the galaxy beyond. The scientists understood that the boundary they sought was not a fixed wall. The heliospheres, shape-shifted with the moods of the sunny, expanding during periods of high solar wind, contracting during its quieter phases. Interstellar pressure pushed back from outside, shaping the bubble into a distorted, comet-like form, with a rounded head facing the galactic wind and a trailing tail stretching far behind. Crossing such a frontier would not be a simple matter of reaching a precise number on a scale. It would be the culmination of conditions both cosmic and unpredictable. And then there was the interstellar medium itself, a place imagined through equations and particle counts, but never touched by human instruments. Far from empty, it was, filled with the ghosts of ancient stars, their exploded remains drifting as clouds of ionized gas. Magnetic fields wound invisibly through that darkness, their lines twisted by the motions of the galaxy. High-energy cosmic rays, born in distant supernova, raced through the void, only to be slowed and scattered when they encountered the sun's outflow. To enter this space would be to step into the true environment of the galaxy, where the sun was just one among hundreds of billions of stars. Still, many wondered, would the Voyagers even know when they had crossed? The instruments had not been designed for this. They carried no camera to capture the view. The only signs would be changes in particle counts, shifts in magnetic field direction, and subtle alterations in the energy of cosmic rays. The data would come in as strings of numbers, cryptic, unadorned, waiting for human interpretation. The crossing itself might happen in silence, unmarked except in the patient pages of telemetry logs. Yet that uncertainty was part of the allure. For decades, humanity's exploration of space had been marked by clear milestones: the first orbit, the first moon landing, the first images of Jupiter's clouds. But this frontier was different. There would be no photograph of the helium number flag planted in alien soil. The moment would exist only in the meeting of mathematics and meaning, in the alignment of signs that told scientists they had left the sun's realm behind in quiet conversations. Some of the mission's engineers admitted to a more personal hope that the crossing would occur while they were still alive to witness it. Many of them had joined the project as young researchers in the 1970s. Now their hair was silvered, their careers nearing their own sunset. The Voyagers had outlasted the predictions of nearly everyone involved, but the clock was still ticking. The spacecraft's power supply, based on the heat from decaying plutonium, declined year by year. One by one, non-essential instruments had to be turned off to conserve energy. The day would come when even the most vital sensors would fall silent, their last signals fading into the cosmic background. And yet, Voyager's continued survival seemed almost defiant, as if the spacecraft carried within it the stubbornness of the species that built it. Across the decades, it had weathered micrometeoroid impacts, the harsh radiation belts of giant planets, and the constant cold of the outer darkness. It had endured without repair, without resupply, sustained only by the precision of its design and the careful commands sent from Earth. That endurance carried a symbolism that reached beyond science. It was a testament to the idea that something made by human hands could not only leave Earth, but thrive far beyond its cradle. The philosophical weight of this journey began to seep into scientific discourse. At conferences, amid presentations, on plasma density and magnetic turbulence, one could hear reflections on what it meant for a machine to leave the solar system. Was Voyager, in some sense, our first interstellar ambassador? Not in the political sense. No one expected it to encounter another civilization, but in the deeper, existential sense. It was a fragment of Earth, carrying the fingerprints of its makers, the languages of its people, the sounds of its oceans and forests. When it crossed the heliopause, it would not only be a scientific milestone, but an act of cultural migration, a symbolic first step into the galaxy. And so, the scientific reactions were layered. There was the careful, methodical analysis of particle data and magnetic field lines, but there was also the quiet awe, the recognition that they were watching a story unfold that had never been told before. In laboratories and living rooms, in university halls and space agency offices, people followed the slow arc of Voyager's trajectory, knowing that somewhere ahead lay a boundary humanity had never crossed. In time, the question became not just whether Voyager would survive long enough, but what we would make of it when it did. Would the crossing be a sharp threshold or a blurred transition? Would it confirm our models of the heliosphere or challenge them? And perhaps most importantly, what would it mean to know, with certainty, that something human-made was now adrift in the ocean between the stars. That answer, when it came, would be more than a line on a graph. It would be the moment when humanity's reach, however faint, had extended beyond the sun's influence, when our technology had carried our presence into the wider galaxy. In that sense, the first scientific reactions were not only about understanding the boundary, they were about preparing for the moment when Earth's voice, through the Voyagers, became part of the interstellar silence. Under the cold and endless silence of deep space, Voyager drifted on. The great planetary encounters were behind it now, the dizzying flybys of Jupiter, the glacial blue majesty of Neptune, the ballet of moons and rings that had once filled its cameras with a flood of images. Those days were gone, archived in the vaults of human memory. Now the spacecraft sailed into a realm where no planet waited, where the only landscapes were invisible, sculpted not in rock and ice, but in the flows of particles and the whispering pressure of the sun's breath. One by one, its senses dimmed. The cameras that had once gazed upon the swirling storms of Saturn were silenced, their heaters shut off to preserve the dwindling energy of the plutonium core. The infrared detectors, the ultraviolet spectrometers, the instruments that once mapped magnetic fields around worlds all were powered down, each shut down a small farewell. What remained was a leaner, more patient Voyager, an emissary not of images, but of invisible data, tuned to listen to the deep cosmic winds that pressed against the edges of the sun's domain. In that darkness, the clues began to appear. Cosmic ray detectors, still vigilant after decades, recorded a slow but steady rise in high-energy particles streaming in from the galaxy beyond. At the same time, the solar wind, once a steady outward breaths, seemed to falter. Instruments measured a subtle slowing of its pressure, as if the sun's influence was running thin, like air thinning near the summit of a great mountain. These were not sudden events, but gentle shifts, patient signals whispered over years, hinting that the spacecraft was approaching the heliosphere's ragged and uncertain edge. Yet the journey carried risks no engineer could touch. Billions of kilometers from Earth, Voyager was far beyond the reach of any rescue. Its systems were aging in the cold circuit, boards brittle, memory banks worn by decades of radiation. The software that had guided it through planetary encounters was reworked, line by line, to squeeze new life from old silicon. Commands were crafted with the delicacy of surgery, tested on earthbound replicas before being transmitted across the gulf of space, knowing each instruction would take over 17 hours to arrive, and another 17 for the reply to return. The connection itself was a triumph of persistence. Earth's Deep Space Network 3, Great Radio. Facilities scattered across the globe had been retooled to catch Voyager's faintest whispers. Antennas the size of office buildings reached into the void, gathering signals so weak they were almost lost in the hiss of cosmic background noise. Even the technology of listening had evolved alongside the probe's journey. Receivers cooled to near absolute zero to reduce static, signal processing algorithms that could reconstruct meaning from the faintest echo. In this partnership between fragile machine and patient planet, the bond had become more than engineering. It was the tether of a shared fate. Year after year, the data came. Not dramatic images now, but long columns of numbers, particle counts, field strengths, energy spectra, each a small tile in a mosaic of the unknown. The scientists learned to read their subtleties, to sense the unseen terrain the spacecraft was passing through. The heliosphere's edge was not a sharp boundary, but a shifting frontier, shaped by the push and pull between the sun and the galaxy beyond. Voyager's readings were maps of a landscape no I could ever see. The decades since its launch had stripped the mission of its early glamour, but replaced it with something rarer: endurance. It had outlasted the lifespan of the teams who built. It weathered the revolutions of science and technology back on Earth, and pressed on into territory no other creation had entered. What remained was not only the pursuit of knowledge, but the slow and deliberate crossing into the wider cosmic sea, a journey whose pace was measured not in speed, but in the stubborn refusal to stop. In this quiet chapter of its life, Voyager had become what it was always meant to be, not just a machine, but a question, moving outward toward the answer. And the answer lay somewhere ahead, in the place where the sun's breath failed, and the galaxy began. The year was 2012. For more than 3 decades, Voyager 1 had traveled outward, away from the warm glow of the sun, into regions where sunlight had thinned to a pale ghost of itself. It had passed the orbit of Neptune, entered the Kuiper belt, and moved far beyond the last planet's grasp. Yet still it remained tethered to the solar system, cocooned within the great magnetic bubble of the heliosphere, a vast invisible shield inflated by the solar wind. Scientists knew that somewhere ahead lay its final threshold, the frontier where the solar wind surrenders to the interstellar medium. The crossing was never expected to be dramatic. No cosmic fireworks would mark the event. Instead, it would be written in numbers, silent changes in the particle counts and magnetic readings, beamed back across billions of kilometers to Earth. On August 25th, the spacecraft registered something extraordinary. The steady stream of solar particles that had bathed it for decades plummeted almost to zero. At the same time, high-energy galactic cosmic rays surged, flooding in from the galaxy beyond. The readings were clear, unambiguous. Voyager 1 had stepped into interstellar space. Humanity had, for the first time, sent a creation beyond the sun's dominion. And yet, one mystery shadowed the triumph. The magnetic field, though stronger, still pointed in almost the same direction as before. The edge of the solar system, it seemed, was not a sharp boundary, but a tangled frontier in the control rooms of the deep space network. The realization sank in with a strange mixture of celebration and awe. The oldest operating spacecraft in history had just delivered the most distant scientific measurement ever made. Yet its signal, a faint whisper barely above the cosmic background, had to be coaxed from the static by antennas larger than buildings. Each bit of data took more than 17 hours to arrive, a journey across nearly 19 billion kilometers. The delay meant the crossing had already happened long before the scientists knew. By the time they announced it, Voyager 1 was even farther. Still, drifting deeper into a realm no machine had ever touched. What the readings revealed confounded expectations. The heliopause had been imagined as a sharp, almost geometric wall, one side ruled by the sun's wind, the other by the galaxy's breath. But Voyager's instruments painted a different picture. The boundary was more like the surface of an ever-shifting sea, marked by turbulence, magnetic eddies, and narrow channels where solar particles and interstellar particles mixed. In some regions, solar particles still slipped outward, as if refusing to yield. In others, cosmic rays streamed inward with no resistance. The magnetic field's direction, so stubbornly unchanged, became the heart of the puzzle. Had the spacecraft crossed into a region where the sun's field was draped and twisted into alignment with the galaxy's? Or was it still threading through some outer filament of the heliosphere, not yet entirely free? The data answered some questions, but opened others wider. Voyager's crossing was no final line in the sand. It was an invitation to reimagine the shape of the sun's influence. In the years that followed Voyager 1's crossing, scientists combed through every bite it had sent, searching for patterns hidden in the noise. The cosmic ray detectors showed an unmistakable permanence in their elevated counts, proof that the spacecraft was bathed in the high-energy particles of the galaxy itself. The solar wind instrument, silent since 1980 due to a malfunction, could not directly measure the outward breath of the sun, yet the absence of its pressure was echoed in other readings. Plasma waves captured through the vibrations of the surrounding charged particles revealed densities far higher than anything within the heliosphere. This was the voice of the interstellar medium, speaking through frequencies that no human ear could hear. Meanwhile, Voyager 2, its twin on a slower, slightly different path, approached the edge with all critical instruments still alive. In late 2018, its sensors confirmed what Voyager 1 had hinted at 6 years earlier. The heliopause was not fixed. Voyager 2 crossed at a different distance under different solar conditions. It recorded the fading of solar particles with a clarity Voyager 1 had not been able to, and it felt the pressure drop of the solar wind in real time. The cosmic ray count rose like a tide, and yet, once again, the magnetic field direction shifted, only subtly. To spacecraft, separated by billions of kilometers and years of travel, had crossed into the galaxy and found a frontier far less distinct than anyone had predicted. The heliopause was revealed as a breathing, restless boundary, one that seemed to blur the idea of inside and outside altogether. The silence beyond the heliopause was not empty. It was alive with the faint, electric murmurs of plasma, the thin, charged breath of the galaxy itself. Voyager's instruments, tuned to sense the trembling of this unseen medium, began to detect something unexpected. The plasma was denser than the models had ever dared to predict. Instead of drifting through a soft and featureless haze, the spacecraft had entered a region where matter pressed more tightly, as though the galaxy's breath here was held in suspension. These plasma waves were more than a scientific curiosity. They were the resonant hum of the interstellar ocean, rolling through space like ripples on an unseen shore. Each oscillation carried a message, a record of pressures, temperatures, and magnetic tensions shaped by events hundreds of light years away. The galaxy was speaking in a language of vibrations, and Voyager had become its first translator. Yet, there were patterns within the data that defied expectation. The magnetic field beyond the heliopause did not simply align with the calm uniformity scientists had imagined. It twisted, forming strange ribbons of intensified strength, arcs of invisible force that might have been sculpted by the Milky Way's vast magnetic framework. Their presence hinted at boundaries within boundaries, a second layer of cosmic architecture beyond the sun's own domain. The contradictions grew. Models had long described interstellar space as placid, its conditions changing only across immense distances. But the readings painted another picture: turbulence, gradients, and shifting densities that suggested this was no still sea. The heliosphere, once thought to be a sealed bubble, might instead be porous, breathing in slow exchanges with the medium beyond. And if interstellar clouds could slip tendrils into this bubble, they might, over geological timescales, touch even the space where Earth orbits, whispering changes into its climate. The sun's magnetic frontier, once pictured as a fixed and impenetrable wall, now seemed more like the shifting edge of a great tide. Voyager's measurements hinted at a heliopause that flexed and breathed, expanding and contracting with the pulse of solar activity. At times, the barrier appeared to swell outward, pressing into the interstellar medium. At others, it seemed to retreat, as though the galaxy's pressure pushed back with unseen hands. These movements were subtle, unfolding over months and years, but they suggested a delicate balance, a tug-of-war between the sun's wind and the currents of the cosmos. The plasma density beyond the heliopause only deepened the mystery. Higher density meant more material, more electrons and ions pressing against the boundary. Some researchers began to wonder if Voyager had entered a region of compressed interstellar gas, perhaps a filament in the larger web of galactic matter. Such filaments, stretched across light years, are thought to trace the paths of ancient shock waves from supernova, where stellar deaths ripple through the galaxy like the aftershocks of a stone thrown into water. And then there was the sound. Converted into audible tones, the plasma waves recorded by Voyager revealed a faint, ethereal chorus, a long, unbroken note that rose and fell with the changing density of the medium. To human ears, it might have sounded almost like wind through the strings of a distant harp. But to scientists, it was a rare opportunity, a way to hear the properties of matter far beyond the reach of any probe before. In this music, there was also warning. The patterns hinted at a region more dynamic than expected, a place where changes in the interstellar environment could propagate back toward the heliosphere. What had once been imagined as a clean separation between sun and galaxy was beginning to dissolve. The two were not strangers, they were neighbors in constant, invisible conversation. If the heliopause was the shoreline, then Voyager had waded into a sea that was anything but calm. The dense interstellar plasma was not evenly spread like a thin mist. Instead, it seemed to surge and shift in pockets, as if stirred by deep, unseen currents. These currents might be driven by the galaxy's magnetic field, a vast, ancient structure woven through the Milky Way, like invisible iron threads in a cosmic tapestry. Some of Voyager's most puzzling measurements came from its magnetometer. When it crossed into interstellar space, scientists expected the direction of the magnetic field to change significantly, aligning more with the galaxy's orientation. But instead, the field's direction barely shifted. It was as though the interstellar magnetic lines were draped over the heliosphere like a taut sheet, held in place by forces not yet understood. This unexpected continuity spawned new theories. One suggested that the heliosphere itself might be leaking porous in certain regions, allowing streams of charged particles to pass through and mingle long before the formal boundary. Another imagined the heliopause as a turbulent mixing layer where solar wind and interstellar plasma swirl together in chaotic VORTS, hints of ribbons or bands, of magnetic intensity beyond the heliopause, only deepened the intrigue. These structures, perhaps hundreds of millions of kilometers across, might trace the shape of magnetic field lines stretched and twisted by the sun's long journey through the galaxy. Like currents meeting in a river, they could form eddies, knots, and braids in the otherwise invisible field. The more data Voyager sent back, the less the frontier resembled a border. It was not a gate to interstellar space, but a zone of negotiation, a place where two immense domains pressed against each other, neither entirely yielding. The heliosphere is more than an invisible bubble of charged particles. It is Earth's first and oldest shield. For billions of years, it has been a quiet guardian, deflecting a ceaseless rain of galactic cosmic rays. those high-energy messengers from distant supernova and dying stars. Without its shelter, the delicate architecture of DNA might unravel more easily, mutations multiplying under the relentless bombardment of interstellar radiation. The heliosphere is a cradle, a womb of charged wind, holding life close to the sun while the galaxy's storms rage beyond. Voyager's crossing revealed that this shield is not a static wall, but a shifting, breathing frontier sculpted by both the sun's pulse and the medium through which it travels. The shape and size of this bubble change over tens of thousands of years, swelling and contracting as the sun drifts through the Milky Way's vast neighborhoods, some sparse and quiet, others dense and turbulent. Every cloud of gas, every magnetic ripple in interstellar space leaves its mark. The heliosphere's form becomes a diary of encounters, the faint echo of a supernova's shockwave, the subtle compression from passing through a dense molecular cloud. Somewhere in its curved, invisible boundaries is a record of our star's cosmic journey, etched in the way its wind meets the galaxy. To step beyond that shield is to feel the raw environment of the galaxy itself, an environment humanity will one day face directly. Without the sun's protective breath between us and the abyss, beyond the heliopause, the stream of cosmic rays is no longer tamed. Out here, the galaxy speaks in a harsher dialect, high energy, protons, heavy nuclei, and exotic particles racing through the void at nearly the speed of light. These are relics of cataclysms far older than Earth, born in the shock fronts of exploding stars and the violent accretion disks of black holes. Their energies are so immense that no man-made accelerator can match them. The heliosphere filters much of this torrent before it ever reaches Earth, but its protection is not absolute. Even within its embrace, cosmic rays seed the upper atmosphere, with showers of secondary particles, subtly influencing cloud formation, and perhaps, as some studies suggest, nudging climate over geological timescales. Outside the boundary, however, the pressure of this radiation mounts dramatically. For future astronauts venturing into deep space, it represents not just a technical challenge, but an existential hazard. Voyager's instruments, long past their design life, now measure this radiation directly, sending back data from a place no spacecraft has ever remained to listen. The increase in particle counts beyond the heliopause is not gradual but abrupt, a sudden unveiling of the true galactic background. It is a preview of the harshness awaiting any crewed mission attempting to cross into interstellar space. In this way, Voyager has become a scout not just for science, but for survival. It has tasted the cosmic wind beyond our sun's reach, and in its aging memory banks, it carries the first detailed record of humanity's exposure to the unfiltered galaxy. The heliosphere is not a static shell. It is a living, shifting bubble, sculpted by the slow voyage of the sun through the Milky Way, like a ship's wake in a restless sea. Its shape bends and distorts under the pressure of the galactic winds. The sun, along with its entire planetary family, drifts through interstellar space at roughly 828,000 kilometers per hour, tracing a vast orbit that will take more than 200 million years to complete. In the path ahead lie regions of varying density, wisps of neutral hydrogen, tangled magnetic fields, and the drifting debris of ancient supernova. Some clouds are so thin that the heliosphere swells outward, inflated like a sail in calm waters. Others are denser, compressing the bubble until its edges press closer to the sun, tightening the shield against incoming radiation. The Voyager data hint at this dance of expansion and contraction. By comparing measurements with models, scientists can reconstruct the invisible environment the Sun has recently passed through. The interstellar medium becomes not just an empty background, but a record of galactic history where stellar explosions left imprints of shock waves, and where long-forgotten collisions between molecular clouds once reshaped the local magnetic fabric. One day, perhaps tens of thousands of years from now, the Sun may enter a denser interstellar region, shrinking the heliosphere to a fraction of its current size. In such a future, Earth's atmosphere would bear a greater burden of cosmic radiation, and life might once again feel the subtle hand of galactic forces. For now, Voyager drifts at the edge, watching this vast, slow dance from its lonely post. The interstellar medium is more than a sea of atoms and plasma. It is the galaxy's memory etched into space itself, every particle drifting between. The stars carries the history of cataclysm and creation. Dust grains hold isotopes forged in the fiery hearts of massive suns long dead. Ions whisper of nearby supernova whose shock fronts once rippled through this region of the Milky Way, distorting the local magnetic field and scattering waves of high-energy cosmic rays. Voyager's instruments, though simple by modern standards, have become archivists of this ancient record. As they measure the density, temperature, and composition of the plasma beyond the heliopause, they reveal that the space between stars is not a quiet, uniform void. Instead, it is streaked with gradients of pressure, abrupt shifts in particle speed, and structures shaped by distant, unseen forces. Magnetic ribbons stretch across the darkness, their geometry hinting at alignment with the galaxy's broader magnetic field. They may be relics of past events, the compressed boundaries of interstellar clouds, or the wake left by a star that once plowed through the medium at supersonic speed. Even the faint hum of plasma waves detected by Voyager is more than background noise. It is the resonance of the cosmic ocean itself, stirred by turbulence that began light years away. Each measurement is a page in a slow unfolding chronicle, suggesting that Earth's neighborhood in space is not fixed, but ever-changing. Over millions of years, these shifting conditions could subtly influence the radiation environment of the inner solar system. A quiet, galactic rhythm in which our planet is just one drifting note, far beyond the comforting glow of the sun, where light itself begins to thin into a dim wash across the void, lies a boundary unlike any seen on Earth. It is not a wall, nor a cliff, but a shifting skin, a frontier woven of magnetism and plasma. Scientists call it the heliopause. To the untrained eye, it might seem still, eternal, but Voyager's journey has revealed it to be alive, breathing in slow, cosmic rhythms. This is no static border. It flexes and sways under the invisible winds of two realms, the solar wind from within, and the interstellar medium from without. The leading view among heliophysicists paints the heliopause as a dynamic interface, more akin to the tide line on a shore than to a fixed marker. Solar activity pushes it outward during energetic peaks of the 11-year cycle, while periods of solar quiet allow the galaxy to press inward. Voyager's instruments, aging though they are, have felt these pulses in the form of sudden changes in plasma density, temperature, and the orientation of magnetic fields. Every fluctuation is a whisper of forces playing out on scales far larger than our solar system, a reminder that even here, on the supposed edge of the sun's influence, nothing is truly at rest. Mainstream theory suggests that much of this restless movement is shaped by the local interstellar cloud, a diffuse, turbulent bubble of gas through which our solar system drifts. The pressure of this cloud, measured in protons and electrons per cubic centimeter, is subtle but relentless, like the weight of the deep ocean pressing against a submersible's hull. The heliopause is its pressure gauge, swelling or contracting. In response to that interstellar push, this pressure does not act alone. It intertwines with the sun's own magnetic field, which extends far past the planets, carried outward by the solar wind like an invisible spiderweb. At the heliopause, this solar field meets the larger, slower, but immensely powerful magnetic structure of the galaxy itself. Where they intersect, their lines twist and bend, creating regions of compression, reconnection, and turbulence. It is here that the orientation of magnetic fields recorded by Voyager becomes a puzzle. For decades, scientists expected a sharp, obvious change when crossing from the solar field to the galactic one, a magnetic signature that would declare, "Beyond doubt, you have entered interstellar space." Instead, the readings were subtle, almost reluctant to reveal the transition. Some argue that the heliopause's magnetic structure is more entangled than imagined, with the two fields interleaving rather than facing each other like opposing shields. This has led to refined models in which the boundary is not a clean frontier but a layered transition, a zone of mixed identities. Supporting this picture are observations from IBEX, the Interstellar Boundary Explorer, orbiting Earth. IBEX detects energetic neutral atoms, fast-moving particles, born from collisions between the solar wind and the interstellar medium. The patterns it records echo Voyager's in-situ measurements, hinting at global shapes and currents that no single spacecraft could see alone. Soon, the IMAP mission will join the effort, offering sharper data, perhaps enough to map the heliopause in 3 dimensions. Yet even the most careful maps will be incomplete. Voyager's detectors, remarkable for their longevity, were built in another era. Their designs bound by the technology of the late 1970s. What they capture are fragments, proxies, the faint outlines of a structure still largely unseen. From those traces, mainstream science builds its best picture, one that is ever evolving. As the sun sails onward into the dark, the limitations are both humbling and instructive. Voyager cannot see the heliopause as an image, nor can it measure every particle and field with modern precision. It senses its environment indirectly through the frequency of plasma oscillations, through the flux of charged particles, through magnetic readings that must be carefully untangled from the spacecraft's own subtle interferences. Each dataset is a partial reflection, like a shard of a shattered mirror, forcing scientists to reconstruct the whole from scattered fragments. Yet, within these limitations lies an unexpected strength. By relying on multiple imperfect tools, the twin Voyagers, IBEX's distant all-sky maps, Earth-based radio telescopes, and soon IMAP's sharper eyes, researchers weave a more resilient understanding. The very gaps in Voyager's data invite creativity, driving models that are tested and refined as new observations arrive. In the mainstream view, the heliopause is not a fixed wall, but a restless membrane. Its position swells and contracts over months and years, responding to cycles of solar activity, coronal mass ejections, storms on the sun's surface, push outward like bursts of breath, inflating the heliosphere. In quieter periods, the galactic medium presses inward again. This slow breathing is not just a curiosity. It determines how many cosmic rays seep into the solar system, influencing radiation levels on planets and moons, and over immense timescales, potentially shaping the habitability of worlds. Voyager's crossing of this membrane is seen. In this consensus, as a first reconnaissance, not the completion of a map, it is a single path through a three-dimensional labyrinth. Every kilometer beyond the heliopause extends that path, feeding the models with precious data. The journey is not merely outward, but toward clarity, a clarity that remains, for now, just beyond the horizon of certainty. Beyond the quiet boundary marked by the heliopause, the darkness seems pure and unbroken. Yet, in certain visions of the cosmos, this frontier is not the edge of a bubble in emptiness, but a strand within a far greater fabric, the galactic current sheet. According to this more radical interpretation, the Sun is embedded within a magnetic structure that spans tens of thousands of light years, coiling through the Milky Way like a vast and rippling ribbon. Within its folds, charged particles drift along field lines that twist under the galaxy's slow rotation. An invisible tide in which entire solar systems drift like specks in a deep and endless ocean. Proponents of this view see the heliosphere not as an isolated shield, but as a shaped and sculpted node within a cosmic power grid, a circuit whose wires are plasma filaments, and whose voltage is measured in billions of volts. While mainstream science acknowledges the galactic magnetic field's influence on the heliosphere, these interpretations lean further, suggesting the Sun's behavior may be subtly governed by the shifting patterns of this enormous electromagnetic lattice. It is a vision where stars are not merely gravitational islands, but luminous beads strung along invisible threads of energy, each vibrating faintly with the heartbeat of the galaxy itself. For now, Voyager's instruments have detected hints of large-scale magnetic field patterns in the interstellar medium, but hints alone. To transform such imagery into scientific truth demands more than poetry. It requires precision and measurements that stretch far beyond the reach of our first raft into the dark. Some see interstellar space not as a serene, frozen void, but as a restless expanse of cosmic weather. Here the winds are not of air, but of charged particles, drifting atoms, and tangled magnetic fields. There are tempests in this vacuum, shock fronts from supernova, turbulent eddies formed where clouds of hydrogen meet the invisible arcs of galactic magnetism. Voyager's passage may be likened to a ship sailing into an unseen storm front, where the only signs are the faint pressure of plasma and the subtle swing of a magnetic compass that has no needle dot. Such a vision reframes the heliosphere not as a bubble in stillness, but as a protective craft forever adjusting its hull against the shifting tides of interstellar weather. A sudden compression of the boundary, a subtle drift in field direction, these could be the signatures of vast, distant events. The detonation of a supernova tens of light years away, the slow collision of drifting clouds that have wandered the galaxy for eons. If true, then Earth's environment has never been fixed. It has always been at the mercy of cosmic weather systems too large for human eyes to see. Among speculative theorists, one question lingers: could such changes ripple down to the delicate climate systems of a planet? Could the Sun's slow voyage through denser or more turbulent regions of the galaxy alter the flow of cosmic rays, and through them, the chemistry of our atmosphere? The notion remains controversial balance between intrigue and dismissal, for the evidence is fragmentary, the connections tenuous. Yet, in science, it is often in these fragile spaces between certainty and imagination where the next great questions are born. From here, the path of speculation leads into stranger territory, into the idea that the galaxy itself may be wired like an immense, invisible circuit, Proponents of plasma cosmology envision magnetic fields and charged particles weaving a vast network across interstellar space, conducting currents on a scale so immense that stars themselves become components in a galactic engine. In this view, the heliosphere is not merely a defensive bubble. It is a glowing sheath of plasma shaped and sustained by the electromagnetic heartbeat of the Milky Way. This concept is far from consensus. Mainstream astrophysics explains the galaxy's magnetic fields through the motions of ionized gas and the dynamics of star formation without invoking a grand electric network. Yet the notion persists in fringe discussions, nourished by the behavior of plasma in laboratories and the peculiar morphologies of distant nebulae that seem to twist like filaments in a cosmic wire. If such a circuit exists, Voyager's crossing of the heliopause might be likened to touching the skin of a vast electrical organism. Every fluctuation in magnetic orientation, every spike in plasma density, could be a local echo of a much larger, more ancient system. The interstellar medium, in this frame, is not passive emptiness, but a charged, living sea, one whose patterns ripple across thousands of light-years. It is here that science must tread most carefully. Beauty and metaphor are tempting companions in the darkness, but without measurement, they remain poetry. The task ahead is to separate the shape of the dream from the shape of the data, to keep imagination alight while holding fast to the anchor of evidence. For only in this balance can discovery advance beyond the shimmer of possibility into the substance of truth. The signal is almost imperceptible now, a whisper threaded through a billion miles of black, so faint that Earth's largest radio dishes must strain against the silence just to hear it. In its tone is no urgency, no fear, only the steady pulse of a machine built to endure. Voyager, the far traveler, still speaks, but the words come slower. The sentences grow shorter. Every transmission is a reminder that time is running out. Its power comes from the slow decay of plutonium, each atom breaking apart and releasing its last warmth into the cold. But the warmth is fading, one by one. The instruments, the eyes, the ears, the senses of this mechanical emissary are shutting down. Not because they are broken, but because the heart that feeds them is weakening. Engineers choose carefully which senses to preserve: the plasma wave detector, the magnetometer, the cosmic rays subsystem. Others go dark forever, sacrificed so that a few may endure. And yet, with what remains, it still reads the deep. It feels the tug of magnetic tides, the hiss of charged particles crossing the heliopause. It listens to the density of plasma in the space between the stars. Each reading is a fragment of a story that will never be told again. Not by Voyager, not in this age. For once its heat is gone, the silence will be final. It will continue to drift, but as a ghost, mute and blind, a monument moving through eternity. On Earth, the race is quiet but relentless. Data arrives in narrow windows, then must be sifted for meaning. Scientists stretch every bit of bandwidth, compressing each packet of numbers until it is almost a code of whispers. They know that the clock is not just ticking, it is melting away. By the 2030s, perhaps sooner, Voyager will no longer have the strength to speak at all. So the question is no longer whether the mission will end, but how much can be learned before that day comes. This urgency has turned attention toward new ways of seeing the heliosphere from afar. Since 2008, the Interstellar Boundary Explorer, IBEX, has been mapping the boundary, not by crossing it, but by catching the ghosts of particles born there. These are energetic, neutral atoms, flung toward us from the interface where the solar wind meets the interstellar medium. IBEX turns them into a picture, not a photograph, but a map in invisible ink, revealing arcs and ribbons that no telescope could see. Even this, however, is only a shadow. Its resolution is to coarse. To capture the fine details Voyager has tasted directly. That is why scientists look toward the future, to a mission that could leap far beyond where Voyager will fall silent. They call it the Interstellar Probe, a ship not yet built, but already alive in the minds of those who dream in trajectories and countdowns. Its goal is audacious, to travel 1,000 astronomical units from the Sun, 20 times farther than Pluto within 50 years. It would not creep outward like Voyager, taking decades just to cross the heliopause. It would surge, carried by the most powerful launch ever attempted, slipping the Sun's gravity with a speed no human-made object has ever known. Its mission would be to map the heliosphere from the outside, looking back at the bubble that shelters the planets. It would take the measure of the interstellar medium itself, feeling the density and temperature of the plasma that laps at our Sun's magnetic shore. It could watch as the bubble changes shape under the pressure of galactic winds, and it would go beyond science alone. It would be a message that even in the 21st century, humanity still casts its gaze beyond the edge of the known. The journey would demand more than technology. It would require patience measured not in years, but in generations. Engineers would build it knowing they would not live to see its farthest discoveries. Scientists would plant questions in its instruments like seeds, trusting that others decades from now would harvest the answers. Such a mission is both science and inheritance. Even now, the groundwork is being laid. The Deep Space Network, with its giant radio dishes spread across the globe, stands as the listening ear of our species. In California, Spain, and Australia, these vast white bowls tilt toward the sky, their surfaces catching whispers from probes tens of billions of kilometers away. From both hemispheres, they can hand off the signal from one to the next, ensuring no spacecraft is ever lost to the curve of the Earth, and the network is not alone. New Horizons, now drifting through the Kuiper Belt after its historic flyby of Pluto, offers another perspective on the heliosphere's outer reaches. It cannot match Voyager's crossing into interstellar space, but it can sample the solar wind far beyond the planets. Comparing its readings with those from IBEX and from Earth's own detectors, every cross-check strengthens the picture, turning scattered data points into a living map around the world. This effort is a quiet collaboration between nations. Astronomers in Japan, Europe, the United States, and beyond share their findings, their instruments, and their dreams. Because the heliosphere is not just the Sun's domain, it is the shield of every planet in the system. To understand its shape, its changes, and its fate is to understand the fragile bubble in which every life we know has evolved in a quiet control room. Hundreds of millions of kilometers away from the spacecraft they monitor, small teams keep the Voyagers alive. The data stream is faint, a fragile carrier wave stretched and thinned by distance, arriving more than 22 hours after it leaves the spacecraft. Every week, it brings just a trickle of measurements: magnetic field strength, plasma wave, frequencies, particle counts. Each value is a fragment of the story unfolding at the edge of the Sun's domain. Power is the enemy now. Both Voyagers, launched in 1977, run on radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium into electricity. But each year, that heat fades, and with it, the current to keep them alive. Engineers have been shutting down instruments one by one. A camera gone decades ago. A spectrometer silent. Each shutdown is a small farewell, a narrowing of the spacecraft's senses. By the early 2030s, even the last detector may go dark, leaving the Voyagers to drift on in silence, still moving outward, but forever mute, yet their legacy will not vanish with their last transmission. The data they have already sent home has transformed our understanding of the heliosphere. They showed us where the sun's influence truly ends, and where interstellar space begins. They revealed turbulence where models had expected calm, and currents of plasma that weave through the boundary like slow rivers through grass. They made the heliosphere real, not just a diagram in a textbook, but a place we have touched. Beyond the Voyagers, earthbound science presses forward. In orbit around our own planet, the Interstellar Boundary Explorer, or IBEX, watches for particles that have traveled unimaginable distances. When high-energy atoms, neutral in charge, slip through the heliosphere and reach Earth, IBEX catches them. From their direction and speed, scientists can infer where they came from, mapping the invisible shape of the sun's magnetic shield. This method has given rise to a new kind of astronomy, one that works without light, instead of photons. It uses messengers born in the chaotic mixing of solar and interstellar winds. The resulting images are ghostly outlines of the heliosphere, like a lantern seen through fog. They suggest a bubble not perfectly round, but warped and asymmetrical, stretched by the forces of the galactic environment. Soon, IBEX will be joined by a successor, the Interstellar Mapping and Acceleration Probe, or IMAP, due for launch later. This decade, IMAP will have sharper instruments, a wider reach, and the ability to track particles that IBEX cannot. It will continue the mapping from Earth's vantage point, while future deep space probes measure the same structures from the outside. Together, they will create the first truly three-dimensional portrait of our cosmic home. Far beyond these technical plans lies the deeper question: why explore at all? The heliosphere is not a tourist destination. It is invisible, intangible, impossible to touch, and yet it may hold the key to understanding the history and fate of life in the solar system. For billions of years, it has shielded Earth from the harshest cosmic rays, shaping the conditions in which life evolved. Its boundary may even act as a filter, modulating the flow of interstellar material into the inner system. Some scientists wonder whether the sun's journey through the galaxy, moving in and out of dense interstellar clouds, has influenced the climate of Earth itself. If the heliosphere shrinks during such passages, more cosmic radiation could reach the planet, potentially altering atmospheric chemistry, cloud formation, even triggering subtle biological shifts. Evidence is fragmentary, but the possibility ties our planet's deep past to the vast motions of the Milky Way. Studying the heliosphere, then, is not only about space physics. It is about understanding the cradle in which our story has unfolded. Under the weightless black, beyond the farthest whisper of the sun's breath, the Voyagers drift. One day, perhaps not far in the measure of decades, their voices will fade. Not because they are lost, but because there will be nothing left to say. The faint radio murmurs that have traveled for over 22 hours to reach Earth will dwindle into silence. And when that silence comes, the planet they left behind will still be turning, seas will still be breathing, and cities will still be alight, yet something will have shifted in the human story. For the first time, a machine we built will vanish not in fire or fracture, but simply by crossing too far beyond the reach of our hearing. Their departure into radio silence will not be an ending, only a transformation. Long after their last signal, they will continue their outward journey, slipping through the slow tides of the galaxy. The sun's glow will shrink to a point behind them, indistinguishable from the countless other stars. In a million years, they will still be moving, not toward anything in particular, but away from everything they once knew. It is possible, however improbable, that one day another intelligence will find them, and if they do, they will encounter a relic from a young species, a vessel carrying the distilled breath of an entire world pressed into a golden record. The symmetry is quiet, almost poetic. In the infancy of interstellar exploration, our first emissaries beyond the sun's domain are not sleek, advanced starships, but artifacts of the late 20th century, spun from aluminum, copper, and hope. They are imperfect, finite, fragile, and yet they are the first to step into the ocean of stars. In the unbroken darkness between stars, there is no up, no down, no sound to mark the passing of time. For Voyager, there will be only motion, a straight, unbending path through the deep interstellar night. Gravity will brush against it now and then, tugging faintly as it glances past the ghostly outskirts of other systems, but never enough to capture it. It will not slow, it will not stop. It will simply drift for millions of years, like a thought that refuses to fade. Long before such distances are crossed, Earth itself will have changed beyond recognition. The continents will shift as they always have. Coastlines will rise and fall with the slow pulse of oceans. Civilizations will appear and vanish. Languages will be born, grow old, and be forgotten. The people who built Voyager will become a faint archaeological trace, and even the records of its creation may be lost to the slow erosion of memory. Yet the craft will endure, preserved in the vacuum like a museum piece sealed in glass, the only witness to a world that once existed in the blue light of a small star. It is a strange kind of immortality, one that is indifferent to the survival of the species that made it. Even if humanity is gone, Voyager will still carry its voice, not in the urgency of a call for help, but in the quiet offering of a greeting. On the golden record, our voices, our music, the sound of wind and water, the cry of a baby, all these will remain, waiting in the dark for someone to listen. Far beyond the faint embers of the outer planets, Voyager will enter a silence so complete that even the Milky Way itself will seem to breathe slowly. There will be no planets here, no asteroids, only the thin whisper of interstellar atoms, a few per cubic centimeter, drifting like invisible dust motes. Cosmic rays will stream past in endless rivers of energy, occasionally striking Voyager's skin, leaving behind microscopic scars in its metal. The slow frost of time will darken its surfaces, its once bright antenna fading to a muted grey, but its shape will remain. It will become a fossil of the space age, untouched by erosion, unweathered by wind. The golden record, sealed within its casing, will endure even longer. Gold, resistant to tarnish, will keep its gleam for billions of years, unless shattered by collision. Etched into its cover are instructions, diagrams meant for minds we cannot yet imagine. They describe how to play it, where it came from, and how long ago it began its journey. It is not a message in a bottle tossed into the waves, but into an ocean that has no shore. If some intelligence finds it, they may learn that a small warm world once spun in the shadow of a yellow star, and that its inhabitants once looked outward, wondering if they were alone. The odds are small, perhaps impossibly so, yet the act itself is its own answer. To send such a message is to declare that even in the face of infinity, we choose to speak. For centuries after its launch, Voyager will continue moving outward, passing the orbits of distant, unseen objects, icy remnants of the sun's formation, drifting in the Oort cloud. These ancient comets, silent and frozen, will barely notice its passing. They are survivors of an age before planets had cooled, before oceans filled, before life began to dream. Voyager will not alter their paths. It will simply share their realm for a short cosmic moment before pressing onward into deeper space. Time will stretch into millennia. On Earth, civilizations will rise and fall. Languages will evolve into shapes unrecognizable to their ancestors, and the continents themselves may drift into new arrangements. Yet Voyager will still be traveling, a steady pulse of motion, following the momentum imparted by a human decision made in the late 20th century. Eventually, the stars will shift. The familiar constellations, frozen to our eyes for thousands of years, will distort as their members drift through the galaxy. Voyager will pass closer to some stars than to others, each encounter separated by tens of thousands of years. None may notice it. Its antenna will be cold, its instruments silent, but it will still carry its record, a fragile archive of a species and a moment in time that once existed under a pale blue sky. And if one day, in some unguessable future, a traveler intercepts it, they may see it not just as an object, but as a question. Who sent this? Why? And what became of them?